All right, we're back. We're on page 89 of analysis. We're solving trig equations, and we pretty much know what we're doing at this point. So let's see if we can do these problems. We want to solve these over the reals, which means not on a limited domain. So all reals got to generalize our solutions. So let's see if we can do it. So here, this one looks very straightforward. Is this a gift? So, I mean, I know that x is going to be pi over 3 plus 2 pi n, and x is going to be, what else, 5 pi over 3 plus 2 pi n, and I know that in both cases, n is going to be an element of the integers. Boom. That was so this is the kind of thing where, like, on the first page, maybe that would have been a struggle, but now we just fly through it, right? Subtract 1. It was so easy, I got to check it. Subtract 1, divide by 2, by negative 2, and then, yeah, pi over 3, 5 pi over 3. Nice. All right, let's see if we can do this. I'm going to add sign to both sides. Subtract 1, divide by 2. Look at this. This one's not bad either. So we have sign and it's negative. So I'm going to say that x is 7 pi over 6 plus 2 pi n, or 11 pi over 6 plus 2 pi n. Well, these are going well. So let's see if they get worse. So here, your potential pitfall is you forget the plus or minus, but we're not going to do that. So I'm going to say that the tangent of x could be positive or negative square root of 3. And since that's the case, I know that I'm dealing with basically all of the pi over 3s. So what can I do here? So if we look at this, we're going to get, pi over 3. But if I add pi to pi over 3, I get 4 pi over 3. And then we also know that we can get 2 pi over 3. But if I add pi to that, I'm going to get 5 pi over 3. So what I'm going to do is I'm going to go with just two answers. I'm going to say that x could be pi over 3 plus pi times n, where n is an element. I don't know why I'm doing that. I'm going to do it for both of them, apparently. And then the other one is 2 pi over 3. There's no way to get it down to just like one formula. And so we're going to need 2, but we need 2 in this case because we're getting all 4 quadrants. Generally speaking, for tangent and cotangent, you only need one formula to generalize your solutions. But here, since we can get plus or minus, we need everything. And I'll do it. You know what I'll do? I'm going to move this one down. There we go. So yeah, like so far not bad. So if you've been keeping up solving these shouldn't be terrible. I mean, they might not be great, but they shouldn't be terrible. What can I do here? So I avoid, like the plague, dividing by a trig function, because if you divide by a trig function, what you're saying is that function couldn't possibly have been 0. But sometimes trig functions are 0. So then you have to think like, well, could it have been 0? And you have to check those solutions. It's like a lot of extra work. So what I'm going to do instead, and you can always avoid it by moving things over and factoring, I'm going to bring the cosecant over. So we'll do minus cosecant. And then this has to equal 0. And then we can factor our cosecant out and get secant minus 1 equals 0. So either cosecant equals 0, which if you think about cosecant, can never happen. This makes no sense. And then another possibility is that secant equals 1. All right, so the reason this can't happen is because this is sort of equivalent to saying that sine of x, I mean, it's exactly equivalent to saying sine of x is undefined. But like sine of x is never undefined. There's no x that you can plug in to sine that will give you undefined. Never happens. So there's no solutions from this part. Let's check this other part. Well, here we're basically saying cosine equals 1. So where does that happen? That happens at 0 plus 2 pi n. So n is an element of the integers. But this problem's a little weird, right? It's got secants, it's got cosecants. I think we should check the answer because I think it's weird. That's how I make the decision. When am I going to check? How weird is the problem? Like, like secant and cosecant both have very different domains. So let's think about this. If x equals 0, then obviously secant of x is equal to, what am I writing here? Let's say if x equals 0, the secant of 0. You know, I don't need this if nonsense. Let's just do this. Let's say check, and I'll do it in a different color. I'll go back to black. Check. All right, secant of 0 is definitely 1. Cosecant of 0. Well, the cosecant of 0 is the reciprocal of sine of 0. This actually doesn't exist. This is undefined. So there are no solutions to this because the only values of x that make the secant of x equal -1, or equal 1 rather, are not in the domain of cosecant. So like they're not in the domain of the function. So this actually has no solutions. Everything was extraneous. That's kind of interesting. I'm just gonna keep going, and then I'm gonna check them all on the calculator at the end, I guess. Let's see. This gives me sine of 3x is going to be, so add 1, divide by 2, that's 1/2. Square root of that is going to be plus or minus radical 2 over 2. All right, so this is like a u substitution situation, or we could say that 3x is going to be all of the pi over 4s because of the plus or minus. Pi over 4, 3 pi over 4, oh, plus 2 pi n's. Should I, all right, pi over 4 plus 2 pi n, 3 pi over 4 plus 2 pi n. I'm going to keep going this way, I guess. 5 pi over 4 plus 2 pi n. And then 7 pi over 4 plus 2 pi n. So it's like, there's a lot of those. And then we'll do n as an element of the integers at the end. So my final answers, because I'm going to divide by 3, are like all the pi over 12s. And then we're only adding 2 pi over 3, because you got to generalize as soon as you can. I'm going to write 3 pi over 12 just to like be consistent, I think. 2 pi over 3n, 5 pi over 12 plus 2 pi over 3n, and 7 pi over 12 plus 2 pi over 3 times n, where n is an element of the integers. Okay, those are my answers to that. And then finally, what do we want to do here? So choices abound. Actually, do they abound, or do I just think they do? I think that what I want to do here is, so like one thought that I'm having is that I would move the cosine over, square both sides. I think that's actually not going to work for us in this scenario. So I think I have no choice but to divide by cosine or sine. I'm going to divide by cosine, and I'm going to get sine of 2x over cosine of 2x equals 1. But the only way that's true is that cosine of 2x isn't 0. So I'm going to say that either of these could be true. Either sine over cosine equals 1, or cosine of 2x equals 0. Because by dividing by cosine, I'm saying it couldn't have been 0. But I'm definitely going to need to check these. So could cosine be 0? I don't know. We'll find out. So this is tan of 2x is 1. So where can that happen? Well, 2x could be pi over 4, but remember it's tangent. So the period of tangent is pi. So I'm going to say plus pi n. N is an element. I don't know why I'm doing this here. Usually I like to say that until the end. So I'm getting pi over 8 plus pi over 2n, where n is an element of the integers. Now let's worry about this. What if cosine was equal to 0? Where is cosine 0? That would be at 2x equals pi over 2 plus, you could just say pi over 2 plus pi n. Could you? Because maybe one of them works and one of them doesn't. So let's not do that. Let's do plus 2 pi n, or 3 pi over 2 plus 2 pi. So I'm like avoiding a potential error. So this would be pi over 4 plus pi n, or 3 pi over 4 plus pi n. So we have to check these. So if I plug in pi over 4, so let's check. So pi over 4 would give me the sine of pi over 2, which is 1, and the cosine of pi over 2, which is 0, so that's out. And then if I did the sine of 3 pi over, I mean, we kind of know that this is, nope, sine 3 pi over 2, because I got to double it. We kind of know this is going to be out too. Cosine of 3 pi over 2 is 0. So the reason that I had to do, so that's obviously out. So we actually get no solutions from this. It didn't contribute anything, which is totally fine. The thing is, it could have. And when you divide by a trig function, you're claiming that the thing you divide by couldn't have been 0. But what if that was a solution initially, right? What if there had been, I don't know, there are scenarios, right? So if you divide by a trig function, you do have to check and make sure that it couldn't have been 0. Could have been 0. Make sure that you didn't exclude the possibility that it was 0, is kind of what I'm saying. So let's check these, and then we'll be done with this page, which is really exciting because we're getting very close to the end of this, which is why we're able to solve the problems like a little more quickly. 1 minus 2 cosine of x. I'm going to be really disappointed in myself if I got this wrong. Expand u. This one is the one where if you add it, you get 5 pi over 3. And then the other one is definitely just pi over 3. So we got that. Let's solve the sine of x plus 1 equals the negative of the sine of x for x. 7 pi over 6 and 11 pi over 6. You can just see it, right? If I add 2 pi to this one, I'm going to get 11 pi over 6. Solve the tangent of x squared, and then minus 3 equals 0. We got to solve that for x. So this gives me, why is this giving me so many answers? Oh, it's adding, is it adding 2 pi's? What? Let me see here. Let's expand this and then add 2 pi. So this is, I think that's really interesting to me that the calculator is giving like every quadrant. So that was, this is the first quadrant. This was the fourth quadrant. And then like it's adding 2 pi. This is amazing to me. So this is going to be, did I already do this one? No. Expand. And if I add 2 pi to this, this will be 4 pi over 3. So that's a third quadrant. Crazy. We got it right, but our answer is more efficient. I don't know why the calculator does it this way. Like it could have combined this answer with this one up here and just said, you know, whatever, like 4 pi over 3 plus pi times n, but it didn't do that. And that's, I don't have an answer for why it did that way. Strange. Let's try this. So we think the answer to this is there is no answer. This one's risky because the domain, the calculator is not amazing at finding domains for these. False, excellent. False means there are no solutions, which is what we thought. Trig functions are tricky, and the calculator also thinks that they're tricky. So sometimes it will struggle to solve a problem like that. So what do we got here? I'm just going to so pi over 12, and then 2 pi over 3, 3 pi over 12, and then it should be 5 pi over 12. Oh, come on. 5 pi over 12, and then 11 pi over 12, which is 11 pi over 12? No. What are you? Oh, no, you're this. Hold on. I think that's 7 pi over 12. Let's see. Let's expand u, and let's add 2 pi over 3, 7 pi over 12. All right, so we got all those, and then one last one, solve the sine of 2x equals the cosine of 2x. So we did this one in kind of a weird way, and the thing I was worried about, I could actually show you. Expand, and then add pi over 2, and we get pi over 8 plus pi over 2 times n. Good. Why do we only, oh yeah, because it's a tangent thing. So like, why do we only get 1 though? So the thing that I was worried about when we had sine of 2x equals cosine of 2x, and then I was going to subtract cosine of 2x from both sides, and then I was going to square both sides, and then expand, and I get this. This is a problem because it doesn't just equal 0, so we can't use the zero product property. So at that point, we wouldn't know how to solve this. So I thought it was better to divide by cosine of 2x, which worked for us. But then we had to check these extraneous solutions. Our goal soon, maybe even the next set of notes, I don't really know, is to figure out like how could we solve this some other way. So that's what we're going to work on. But anyway, we're done with this page. So I'm going to come back in the next video. So if you look in the notes, there's some extra practice problems here you might want to do. And you can check them on your calculator. These all have a finite domain. So I'm really glad that I didn't have to do those. Looks like some factoring is involved. That's great. Yeah, like definitely do these. These look like good problems. Ooh, trig identity problem. Yeah, those you should definitely do. But anyway, I'm not going to do them. I'm going to leave them for you, and I'll be back in the next video, and I will see you there.